In this video, I'll be describing the analysis of 5 pads where we measured 4 positions in each pad. I think I will start out by first describing aspects of the user interface. We'll show some data displays and some user input screen prints. I'll describe those in detail. Then we'll go on to making a measurement and look at the mechanics of inserting the pad and initiating the measurement process. And then lastly, we'll look at the report data. This is the main screen that is used to set up the measurement process. At the far right, there are 3 dialog boxes: ID1, ID2, and ID3. ID1 and ID2 are used to name the file name, and ID3 is left as open for user to put in any input, and many times we'll put the transducers that we used. In the middle section, there's user input data. The batch ID is generally the name of the pad. The sample number is automatically incremented, or the user can put in a sample number. Operator is initials. Number of positions. The current system can tolerate up to 8 positions to be measured per pad, and as few as 1. Target load is set by the user. Here it's set at 700 newtons. It can be ranged from 100 to 800 newtons. Normally, we default to 700. The user needs to independently measure the backing plate thickness for each pad being looked at. And if there is a shim, you can put in the shim thickness, but you need to be aware that there has to be additional calibration for the shim velocity. And then the friction material density, we default to 1 gram per cc. If you know the density ahead of time, you can put in the actual density of the friction material. Otherwise, all of the data will be computed using the 1 gram per cc, and you can add the density as long as you use these units at a later date. The control functions here, the start measurement actually initiates the measurement process. There's also a calibration procedure that I'll discuss in another video. And then there's a setting, and then there's a special mode, which is not used very often, which is a switch to cycle, where we measure the modulus of the material as how it changes with loading. This is the file management box. This box appears when the first measurement is made. And what it does is concatenates the ID1 and ID2 user entries, user inputs, and that's used to form the file name. The files are stored in the documents iETEK directory. And if you want to change the name, you can do that, and then you can hit OK, and the box will disappear. All of the report data will be stored in this file. This shows the raw ultrasonic data display, and we call it the debug screen. When you press the measurement button, this raw data display will show up. It is optional. We normally monitor it while we're taking the measurements to sort of visualize the ultrasonic data, but the user can turn it off if they would like. In addition to the raw data display, there are boxes in the lower portion of the display which measure the amplitude, the gain that is needed, the waveform acquisition time, and the preload number. Okay, I'm going to go through and quickly show you how we generate the measurement on 5 different pads measuring 4 positions on each pad. First of all, just to explain the instrument, the gray panel contains all of the electronic components for the iETEK. That's the A to D, the ultrasonic pulsar and receiver, the motion control, as well as the load conditioner. The external components are indicated by the arrow. You have the stepper motor, which is on top, and then with a long lead screw controls a platform that has the transmitting and receiving transducers located here, and the housing that locates the lower transducer has a load cell which measures the preload. And then we have the user interface and the raw data display shown in the arrow. We can then just, this slide shows sort of a close-up of the transducers. The lower transducer is raised up just slightly above the surface of the sample holding platform, and the upper transducer is aligned collinearly so that when load is applied, the brake pad seats with the transducers and the load is provided directly through the transducer interface. To look at the measurement process, here we have the same setup. The pads will eventually find their way between the 2 transducers. The user is keying in some of the data in the user interface. The file names is identified here, and you need to put in the sample or the backing plate thickness and the sample ID. When you make the first measurement, the dialog box comes up, which shows you where the report file will be. I'll have some close-up of the user interface so you can actually be able to read on the screen. But in this particular view, I just wanted to illustrate how the samples are loaded and unloaded. So the samples are put in this sort of vertical orientation and then moved manually from one position to the next. In this case, we measured 4 positions per pad. So there is a user-specified preload. In this case, I think we sort of have standardized on 700 newtons, and it's servo-controlled, so it controls the preload fairly precisely. She just changed out the pads, and all she had to do is put in a new pad ID and a new backing plate thickness. All of the timing data that comes out of the iETEK, the time of flight, the TOF numbers, have the backing plate thickness, the transit time subtracted. So the data that comes out does reflect the properties of the friction material and the influence of the backing plate thickness and its velocity have been removed from the data. I'm going to speed this up a little bit so that you can, so that we can get through all of this. And I'll just show you. We're going to measure a total of 5 different pads, and I wanted you to be able to see how that goes. Now, the actual measurement process, once the load has been, the preload has been put in place, is actually quite fast. It takes about less than 300 milliseconds to actually make the measurement. In the previous segment, we concentrated mostly on loading and unloading of the pads, and the user interface was not very visible. In this segment, I want to look at the user interface in a little bit more detail and describe the interaction of the user with the user interface. The panel at the far left contains three blank boxes. ID1 and ID2 are used to name the file. ID3 is blank, and the user can put that the other documentation information in, and that will propagate into the report file. In the middle section, there's measurement information, the batch ID, or we also call it the sample ID. User inputs that. Sample number can be input or will increment if the batch ID is the same. So if you're measuring 10 pads of the same sample type, it will automatically increment that. The operator input, the name of the operator is put into this box or into the operator box. The number of positions can be up to 8 positions and a minimum of 1 position. In this case, we'll be measuring 4 positions for each pad. The target load, we use 700 newtons typically, but you can change that from 100 to 800. The backplate thickness needs to be measured independently and entered by the user with the millimeter designation. The shim thickness defaults to 0. If you have shims and you make measurements with shims, there will be special calibration procedures that one will have to use to account for the shim velocities. And then the friction material density, we default to 1 gram per cc. All of the data on modulus comes out in megapascals per gram per cc. So if you want to recover the true modulus, you have to multiply by the density. The measurement process is initiated simply by clicking the Start Measurement button. So we'll turn this on and we'll show you the interaction. So the user inputs the ID1 and ID2 numbers, which will generate the file name designation. Then in terms of user input, you have to identify what pad you're looking at. You can leave the sample number blank. It will start at 1, number of positions, the preload, 700 newtons, and the backplate thickness. Once you press the Start button, then a dialog box will come up, which will designate where the file is. With the measurement button, we have the raw data display that shows up to the far left. This data will start out as blank, and then it will scroll looking for the appropriate echo and changing the gain of the system between various scrolls. Once it gets to an acceptable level, it will lock on to the signal and make the measurement, and the measurement results are shown in the table. The thickness, the load, the time of flight, and the modulus numbers. And again, the time of flight, called the corrected time of flight, because we've removed the, excuse me, we've removed the contributions from the steel backing. So each time the measurement is made, the load retracts, you pull the sample out, you replace it with a new sample. When a new pad type is put into the system, you need to change the batch ID. You also need to change the backplate thickness. You hit the measurement again, and the new pad is put in and measured. So, um, okay, we're going to measure all 5 different pad types here. So I'm going to speed up the process a little bit so that you can get some idea of the range of modulus that we see. We use these 5 pads in order to, I won't say calibrate the system, but we use this to sort of verify operations. These 5 pads are measured on our machines when we make either new machines or when we change out transducers just to verify uniformity of the results. So I'm going to speed this up a little bit so that we're not waiting for a long period of time. We'll just, again, 4 measurements are made per pad. This particular one has a fairly high modulus. We enter in a new pad type, change the thickness, press the measurement button, and generate a new set of data. And then finally, we'll look at the last one of the 5. And that would complete the set. I'm going to briefly describe the report format. A more detailed description of the report is given in the user manual. The reports contain all of the user input data as well as all of the measured data organized by position and sample. Specifically, the time of flight, the thickness measurement for each position, and the calculated modulus for each position, as well as the average for each of the pads. The format is shown here, and the cursor shows some of the important header information, the modulus scale factor, calibration offset, and the brake pad velocity, which are used in the modulus calculation. And then we have several columns: the date, time the measurement was made, the ID3, which is an optional, user can either leave it blank or input it, the batch ID, sample number, operator initials or names. Positions can be up to 8 positions. The target load, the brake pad thickness, which needs to be measured independently, and then also a shim thickness if a shim is available, and the density, which we set to 1. You can change that to the real density. Then each position, we have a measure of the total thickness of that position, the time of flight, and the Young's modulus. And as we go to the right down the page of the Excel sheet, you'll see the data for position 2. And then as I scroll over, position 3 and position 4. There are 4 positions blank, which are calculated, but if there's no data, then they're left blank. And then we have a pad statistics number where we reproduce the sample ID, the pad thickness, the standard deviation of the thickness within the pad for each position. Density is just reproduced. The modulus for each position, or our average modulus of the pad, and the standard deviation, and then the gain used to make the measurement. The calibration offset the gain used on the calibration sample, and then the thickness calibration number. And then further to the right, we've sort of summarized the modulus by position, as well as recomputed the statistics for each of the pads. In this case, there are 5 different pads used. And then we also record some amplitude information far out to the right. This is not used in any of the calculations, but provides us with some diagnostic